Hi, everyone, and welcome to the defense of my PhD thesis, Data-Driven Pitch Content Description of Choral Singing Recordings. This is work that I've been doing in the last 4 years, roughly, at the MTG in Universitat Pompeu Fabra, together with Emilia Gomez, my supervisor. And before I start the presentation, I would like to take this opportunity to thank Rodrigo, Jordi, and Joanna for accepting our invitation to be part of my thesis committee. So before I start with the presentation itself, I want to give a some quick context about what I will be talking about in the next roughly 50 minutes. This thesis is focused on choral singing recordings. So we will be talking about choir music, and specifically we study the pitch content of this choir music, of these recordings. So we will be trying to extract the frequencies, the notes that the singers are singing in the choir performance. And we are using data-driven techniques to study the pitch content of these recordings. And now that we know what I will be talking about, let me give some context and some motivation about why we are focusing on choir music and why is vocal music so relevant. So choral singing is one of the most extended forms of musical performance around the world. And there are, according to the European Choral Association, there are more than 37 million active singers in Europe. And according to Chorus America, there are more than 54 million active singers in the US. So as you can see from these numbers, they show some potential, or they show that choir music or research on choir music can be relevant and can impact a large number of people around the world. There are some research studies also that prove that singing in a choir has some sort of benefits, some social benefits, such as the feeling of belonging to a group or to a community, some physical benefits such as improved breathing capacity, for instance, and also some mental health benefits such as stress reduction. Computer-assisted tools, technological tools are not yet extensively used in the world of choir music. Choirs are not extensively using technologies to support their practice in general. So there's here an opportunity for the music information retrieval community to develop tools and technologies that choirs can use in their practice or for their preparation of their repertoire, for instance. Some examples of potential technologies that we could develop are systems for the automatic transcription of choir recordings, so that given a performance of a choir, a recording of a performance of a choir, we can automatically transcribe this audio recording into musical notation, so into scores, so that we can use this score for further practice, so that we can, for instance, sing it afterwards again. We can develop some practice tools, so we can, for instance, develop a system that assesses the performance of a singer automatically and gives some feedback to the singer about the quality of the performance. And other applications that we could build are, for instance, extracting information automatically about the performance to support musicological research. In this thesis, so there are many choir types and forms, and in this thesis, we focus specifically on the most common definition of a choir in the Western music tradition, which is commonly multiple singers singing simultaneously and divided into 4 sections according to their vocal range, to their tessitura. These sections are specifically the soprano, alto, tenor, and bass. So we will be talking about mostly the well-known SATB choir configuration. Choral music poses some challenges from the computational analysis of recordings in terms of pitch. So we identified 4 main challenges in the context of this thesis. The first challenge that we want to mention here is the lack of annotated data for research on choir music. When we started this research back in 2017, there were nearly no open datasets of choral music that we could use for our research. The second challenge that we identified is the fact that in a vocal ensemble with multiple singers, the singers have very similar timbres between them. So if we compare a vocal ensemble of 4 singers, a vocal quartet, for instance, to a pop rock band, where we have vocals, we have guitars, we have bass, and we have drums, just as one example. In the pop rock band case, each of the instruments has quite different timbres, so they are easier to discern because of this. But when we focus on a vocal quartet, we have different people, but they are all singing. So this is all singing voice signals, which have more similar timbres. So they are more challenging to study separately and to discern. The third challenge that we identify is that in choir recordings, there's a high harmonicity between the voices. This is related to the second challenge, because most choral music is specifically written for singers to harmonize with each other, for voices to harmonize with each other. But when we look at a choir recording from a signal processing perspective, what we find is a significant amount of overlapping harmonics because of this this musical feature that choir voices harmonize with each other. So these overlapping harmonics are all make the study of singers independently also more challenging. And the last challenge that we identify from choral music is the presence of unison performances. So a unison in this context is when two or more singers sing the same note at the same time. And in choir music, we find both intersection unisons and intersection unisons. So an intersection unison is, for instance, when all sopranos from a choir sing the same note at the same time. So all the singers of a section in a choir usually sing in unison. And an intersection unison is when all sopranos and all altos from a choir are singing the same note at the same time. So this is also challenging from the pitch content analysis perspective. After studying the related literature and its limitations around choir music, we defined the goal of this thesis as to extract pitch information from each singer of a vocal ensemble so that we can use this information for further tasks, such as the automatic transcription, as I was saying before, pitch-informed source separation, or intonation analysis as among other tasks that we could use this information for. To achieve this broad goal of this thesis, we address multiple tasks that are summarized in this figure. The first task that we address is the data generation, because as I said at the beginning, when we started this research, there was a lack of data, so we needed to create new data sets for our studies. The second task that we address is multi-pitch estimation, which essentially consists of given a polyphonic input audio recording, we extract all the F0s, all the frequencies, all the notes that are active at each time frame of the signal, and we output a multi-pitch stream, which has multiple F0 values per frame, but no indication of the source of each of these values. So we obtain the notes that the singers are singing in the performance, but we don't know which singer is producing each of the notes. And given the limitation of the fact that with multi-pitch estimation, we don't know the source of each note or of each pitch value, we explored also the task of multi-pitch streaming, which is closely connected to multi-pitch estimation. But in this task, we not only estimate the frequencies or the pitches that are active in the signal, but we also group them according to the source where they belong. So at the output, instead of obtaining a multi-pitch string, we obtain 4 monophonic independent pitch contours, 1 for each of the sources in the input ensemble. In a similar way, we also address the task of voice assignment, which in our work in particular takes as input the output of a multi-pitch estimation algorithm and specifically assigns each of the predicted frequencies to its corresponding source, obtaining, as we obtain with multi-pitch stream, independent pitch contours for each of the singers in the ensemble. And finally, we conduct 2 experimental studies on the characterization of vocal unisons in terms of pitch and specifically in terms of pitch dispersion. This is the outline of the presentation. So these are the parts that I will be covering throughout this presentation. And let's start with the first step, which is the data generation. So as I mentioned earlier, when we started this research, there were not a lot of datasets that we could use. In this table, you can see a summary of some existing datasets of polyphonic vocal music, but they had some limitations. So some of them were not publicly available and we required open data for our research. Some of these datasets only contained room microphone recordings. And for our studies, we actually needed or we wanted to have multi-track recordings of vocal ensembles so that we could study the contribution of each singer separately. And with room microphones, this is very challenging. Some of them were very small, and since we are dealing with data-driven techniques, we needed more data for our research. And the 2 last datasets that are in this table are focused on Georgian vocal music, and this is out of the scope of our thesis because we are focusing on mostly SATB choir ensembles. So given the existing datasets limitations, we planned some datasets that we wanted to create and release. It was very clear to us that the dataset had to be multi-track and publicly available. And then we wanted to cover different characteristics. For instance, we wanted to record multiple singers per part. So for each of the SATB sections, we wanted to record several singers. We wanted to use different microphones and ideally at least 1 individual microphone per singer. And we wanted to cover different songs in different languages, also including different types of annotations in the dataset. And we also planned to record both professional and amateur singers. And following these requirements, the first dataset that we created and released is the Choral Singing Dataset. for which we recorded a choir of 16 singers distributed into SATV sections. This dataset has 3 songs and in 3 different languages, and the singers that we recorded were semi-professional. I have 2 audio examples for this dataset. The first one is a soprano recording. And the second example is a bass voice recording. The second dataset that we that we released as part of this dissertation is the ESMUC Choir Dataset. In this case, we recorded 12 professional singers with individual microphones and also captured the overall choir sung with 2 different room microphones. And we recorded multiple takes of 3 songs in German. And in this case, we have a larger dataset. So we obtained half an hour of audio compared to the Choral Singing Dataset, which had 7 minutes of audio. I have 3 examples of this dataset. First, a room microphone recording. And now an alto and a bass recordings.
Christi, heilige mich. Heilige mich.
The third dataset that we published, recorded and published is the Dagstuhl ChoirSet that we created together with our collaborators from Audio Labs in Germany. In this case, we recorded 13 mostly amateur singers, distributed also unevenly into SATV sections. And we recorded multiple takes of 2 different songs plus some vocal exercises. And the songs are in 2 different languages. And one special feature of this dataset is that we used these special throat microphones also for the recordings that we will hear in a minute, an example of. And this is the largest dataset that we created because it has almost 1 hour of multi-track audio. We have 3 examples. First, a room microphone recording of a quartet performance. Now we can hear an example of how a throat microphone sounds for a tenor singer specifically. And finally, a recording of a soprano with a dynamic microphone. The last dataset that we created and released is the Cantoría Dataset, and this one is different from the other 3 because in this case we didn't record a choir, but we recorded a vocal quartet, a professional vocal quartet from Spain called Cantoría. So we only recorded 1 singer per section. We recorded 11 songs in Spanish, and the dataset also contains some pitch annotations. And I have 3 examples from this recording. First, a mixture of the quartet.
Sus, no más dormir, cantemos aquí lores in.
Now a soprano and a tenor.
Sus, no más dormir, cantemos aquí lores in paz.
Sorry.
Sus, no más dormir.
Yeah, okay. Let's keep the tenor recording because now it's a bit difficult to just play it independently. So after creating all these 4 datasets, if we combine them all together, we obtain roughly 2 hours of multi-track audio covering different languages or multiple languages, different types of microphones, different annotations. And the also very important part is that they are all publicly available and multi-track. Okay. Now we move to the second part of this presentation, where I will discuss our work on multi-pitch estimation, which was presented at ESMUC 2020 and which was done in collaboration with Brian McPhee at NYU. So we start with an overview of the proposed system for multi-pitch estimation, which is based on the deep salience method for general purpose pitch salience estimation developed by Bittner and colleagues a few years ago. So we propose an adaptation of pitch salience for vocal quartets, specifically given an input recording of a 4-part a cappella vocal ensemble, always restricted to SATV voices. We calculate some audio features, and then these audio features go through a neural network, a convolutional neural network specifically. And then this network, instead of predicting directly the multi-pitch streams, so the pitch values, it estimates a polyphonic pitch salience representation of the input. And this representation has a ideally has high salience in the time frequency bins that belong to the melodies present in the signal, and is 0 or very low salience in all the other bins in the representation. And then this salience representation is post-processed and converted into the output multi-pitch stream, which is the final output of the full system for multi-pitch estimation. To train our system, we compiled existing datasets of vocal quartets. So we focused on vocal quartets to be able to generate more data for training, so that we created all possible signal combinations, always restricted to SATV mixtures. And after creating all the signal combinations, we ended up with 56 songs and multi-track audio of roughly 3 hours. But this was still not enough data for training deep learning models. So we performed some data augmentation in the form of pitch shifting and adding artificial reverberation. And after the data augmentation, our dataset had over 150 hours of quartet recordings. In terms of input features, we followed the deep salience work, and we selected the harmonic constant Q transform as one of the inputs of our network. So we are dealing here with the magnitude of the HCQT, and we decided to add a second input to the network, which are the phase differentials. And we decided to add this second input to the network, besides also using the magnitude, because the phase differentials are used to calculate the instantaneous frequency. And we had this hypothesis that using the phase differentials could yield better results than only using the magnitude. The targets that our network uses to train, and the targets that our network outputs, let's say, are what we call ideal polyphonic pitch salience representations. As I said, these representations have high pitch salience in the bins from the melodies and are 0 otherwise. We create these 2D representations directly mapping the pitch contours that we find in the datasets to this 2D representation. And these targets have the same shape as the input, so that we can directly map one bin from the input to one bin from the output of the network. This is the network architecture that we propose. We call it late deep. And it follows the deep salience approach, because in this case, 2 of the layers of the network, which are indicated in orange in this figure, we replace the more traditional square convolutional filters that are commonly used in convolutional neural networks by vertical filters that cover slightly over 1 octave in frequency. And we decided to use this approach so that these vertical filters can help discern different frequencies and different harmonics to obtain the final multi-pitch output. The last step of the proposed methodology is the post-processing, where for each of the frames of the polyphonic salience representation, we find the peaks, and then we apply a threshold, and the peaks that we found that are above this threshold are converted into their frequency values and output in the multi-pitch stream. This threshold is optimized on the validation set after training the model. We conducted some experiments to assess the performance of the proposed method. In particular, in this case, I'm summarizing the results of some experiments on the barbershop quartets dataset, and I'm reporting in this table, as you see, the average F score. We compare the performance of the late deep model to 2 different baselines for multi-pitch estimation in vocal quartets also. Specifically, we are using the M-singers and the vocal 4 systems, both of them based on spectral and factorization. And what we find here is that the late deep outperforms both baselines on the barbershop quartets dataset by at least 8% average F score. And this indicates, the late deep was the first deep learning based model for MPS, for multi-pitch estimation in the context of vocal quartets. So these results suggest that actually using data-driven techniques in this task can outperform the existing baselines, which are not entirely data-driven. In this slide, I want to show you an example of the output of late deep on a song from the Cantoría Dataset, which was not used for training the model. So the top part of this figure shows the output polyphonic salience representation, where we see already most of the melodies detected, at least. And we can listen to the input mixture so that you have an idea of how the input signal sounds like.
Y oiremos que mañana ayunaremos por honra de San Antruejo paremos.
And in the bottom figure, we see the output of late deep plotted in black, and the color trajectories correspond to the ground truth for each of the voices in terms of pitch. we see that most of the pitches are correctly predicted, at least from this figure, but we can listen to the sonification of the late deep outputs for this same excerpt that we've just listened to. One thing that we notice in the sonification and also from the figure, which is maybe easier to see, is that late deep is capable of correctly predicting large vibratos and voice fluctuations in terms of pitch. And I say large vibratos because the late deep has a resolution of pitch of 20 cents. So when the vibrato allows to be predicted with this resolution, late deep is capable of predicting it correctly. And what we also see is that there are some pitch jumps. We see some black points around second 7, for instance, around here, which are a post-processing problem that could potentially be improved, but late deep has some discontinuities sometimes in the outputs. I have another example for from late deep's outputs that shows or that points to one limitation of the model. So in the top part of the slide, I'm showing a figure of the outputs of late deep on a recording from the Dagstuhl ChoirSet, and specifically here we have an artificial quartet mixture. So we are combining together the individual recordings of each of the singers of a quartet that sounds like this. We already see from the figure, so the prediction is are the green parts of the green part of the plot. We already see that the results are mostly correct when we compare them to the black ground truth. We can listen to the sonification of these outputs now. And when we look at the second example, which is depicted in the bottom part of the slide, in this case, we have an example of the same song performed by the same singers, but instead of inputting an artificial mixture of a quartet, we use the recording from the room microphone that sounds like this, and it has some room effects. So it's the same performance, but there's some reverberation and some room effects that make it sound quite different. And when we look at the outputs already plotted in the figure, we see some problems. If we focus on the alto voice, which is this part here, this line, we see that the alto comes and goes, so the prediction is missing some frequencies. And we see that this is very different from the top plot for the same song. So this is not related to the song or to the music material, but it's rather related to the acoustic conditions of the recording. So we already see that the alto is problematic here. And we can, if we listen to the sonification of the outputs, we will also perceive or we will hear that the alto appears and disappears constantly throughout the excerpt. So this comparison between these two inputs points to one of the limitations of late deep, which is when we have this kind of acoustic conditions with stronger reverberation or stronger room effects, the model struggles to predict especially the inner voices. This is just one example, but in other examples we see that the tenor also has some problems sometimes. And to conclude about this second part of the presentation, we developed a system for multi-pitch estimation specifically for vocal quartets that outperforms two baseline systems for on the same dataset, the barbershop quartets dataset specifically. And we included the phase differentials as a second input to the network. And we also evaluated a version of the model without the phase differentials. And we found that indeed the phase information improves the precision in terms of multi-pitch estimation, but the difference is not very large. So including the phase makes the model significantly larger, but it doesn't improve the performance equally largely, let's say. In terms of limitations, the main limitation that the multi-pitch estimation model has is the fact that it's trained with artificial mixtures of stems. As we've seen in this last example, when we use an input signal, when we try to predict the pitches with an input signal that has a bit of reverberation or some room effects, the model is worse than when we input artificial mixture of the stems, which makes sense because the signal is cleaner and it's a dry signal when we just mix individual close-up microphone recordings. The second limitation that we find in this method is that the dataset that we use for training has a lot of redundancy because of the data augmentation. We've also seen in one of the examples that the output multi-pitch stream has some pitch jumps and some discontinuities. And this is especially perceivable when we sonify the outputs. And as all multi-pitch estimation systems, these have the usability of their output is quite limited because we only have information about which frequencies are present in the signal, but we don't know the source of each of these frequencies. So if we wanted to use this information for further tasks, such as guiding a source separation algorithm, we would first need to know the source of each of the estimated frequencies. And as I said at the beginning of the presentation, this limitation of not knowing the source of each of the frequencies led to exploring the task of multi-pitch streaming. And this is what I will talk about now in this third part of the presentation. This is an overview of the system that we propose for multi-pitch streaming. And as you can see already, it looks very similar to the system that I just presented for multi-pitch estimation. Given an input recording of a 4-part vocal ensemble, we calculate some audio features, and these features go through a neural network, deep learning network, and then this network outputs, instead of a polyphonic pitch salient representation, as we've seen with the late deep network. In this case, for multi-pitch streaming, we propose a network that outputs 4 monophonic pitch salient representations, so that the contribution of each voice is present in each of these separated outputs of the network. And then each of these representations is post-processed and converted into 4 independent monophonic pitch contours. So at the output, we obtain not only the frequencies, but they are grouped together according to their singer, to their source. For training our method for multi-pitch streaming, we use the same dataset of vocal quartets that we use for multi-pitch estimation and all the augmentation steps also. And in this case, we are using a more complex deep learning network. So we decided to use a simpler input feature, audio feature. So we are, instead of using the harmonic constant Q, magnitude, and phase differentials, for the multi-pitch streaming, we propose to use just the magnitude of the constant Q transform. So we only use the magnitude of the CQT as input to our network. In terms of the output targets, we create them the same way as we created the output targets for multi-pitch estimation. But in this case, since they are monophonic, we just map them directly. We just map directly one pitch annotation from one singer to one monophonic target for each of the songs and each of the singers. For the multi-pitch streaming, we propose the use of a UNet-based architecture. So we take some inspiration from a model for music source separation that uses the UNet architecture to predict time frequency masks to separate, for instance, the vocals. The main feature of this UNet architecture, so the standard UNet architecture has an encoder, decoder shape, let's say, shape. And in this case, we propose to have one encoder and then 4 separate decoders, each of the decoders in charge of predicting one of the monophonic salient representations. A special feature of this network is that following our work on multi-pitch estimation, we replace one of the layers. So in one of the layers from the encoder and in one of the layers from the decoder, we replace the square convolutional filters by vertical filters. And these layers are indicated in orange and blue for the encoder and the decoder. We evaluated the performance of the unit that we propose, which we call harmonic unit, also on the Barbershop Quartets dataset, and we are reporting here as a summary the average F score that we obtain on this dataset, and we compare the performance to the vocal 4 baseline, which also performs voice assignment, so we can evaluate each of the voices separately. The first thing that we notice from these results is that the bass obtains the best performance, and so the harmonic unit obtains the same performance as the baseline for the bass. It is 84% in F score. And for the other voices, what we see is that the proposed harmonic unit outperforms the baseline by different margins. And this is the voice-specific evaluation where we can just evaluate each output against the monophonic ground truth for each of the voices. We can also combine the outputs of the harmonic unit together into a multi-pitch stream and evaluate these against multi-pitch estimation ground truth, and we can compare the overall multi-pitch estimation performance to the late dip and to the baselines that we've seen before, also on the barbershop quartets dataset. And in this case, what we see is that combining the outputs of the harmonic unit together yields worse results than those that we obtain with the late dip. When we think about this, it actually makes sense because we are using the same dataset for training two models, one for multi-pitch estimation and one for multi-pitch streaming. But the multi-pitch streaming task is clearly more challenging because we not only estimate the frequencies, but we also assign them to their corresponding source. And this is more challenging given the same amount of data. This example that I will show you now exemplifies or illustrates one of the limitations that we found from the harmonic unit. In this, these are the monophonic outputs from the harmonic unit, and highlighted in this red square, we see that the soprano output has no energy in the last two notes. So this square corresponds to the last two notes of the song, while the other voices have energy in this last part. And I can tell you that in the input recording, the soprano is singing two notes, just as all the other voices are. So to understand why this happens, we can look at the final output of the multi-pitch streaming system. And then in this plot, in the darker colors correspond to the ground truth pitch contours, and the lighter colors correspond to the predictions. And what we see here, by looking at the ground truth, is that the last note of this song is a unison between the bass and the tenor voices. But when we look at the predictions, this unison note is only predicted in the bass voice, and then consequently the tenor is predicting the alto note, and then the alto is predicting the soprano note, and the soprano voice is empty. And this is why we've seen already in the salience, monophonic salience from the soprano, that there's no energy in the last two notes. This is an example of this limitation that the harmonic unit has, which is that when there's an intersection unison, so two different voices singing the same note, this model is not really capable of assigning the note to two different voices. So the unison note is just predicted in one of the voices, and then the rest are usually assigned following the pitch height order. There are other examples where other things happen, but in most cases, this is what we see in the outputs. We have one example here from the same song that we've seen already for the late dip model for multi-pitch estimation. In this case, since we have independent outputs, we plot the outputs in different colors also. And we can just hear the input mixer again for reference.
Y oiremos que mañana ayunaremos por honra de San Antruejo paremos.
Okay. Then in this first part that I'm highlighting here, what we see is that the alto voice is predicting the two soprano notes, and then the soprano voice is empty. So it should be predicting these notes, but the alto is predicting them, so the soprano is left empty. And then consequently, the tenor is predicting here the alto voice, leaving the tenor note empty. So this is not a unison as we've seen in the last example, but when there's one note assigned incorrectly, then usually the notes that follow for a while are also incorrectly predicted. And this is a behavior that we see with the harmonic unit. And then in this second part that we're highlighting here, this is a unison between the soprano and the alto voices. And in this case, we see that the soprano is mostly empty, and this note from the unison is only predicted by the alto branch of the network. We can listen to the sonification of these outputs, but since in the sonification we hear all the voices at the same time, there are some mistakes that we can't perceive, but if we listen carefully and compare it to the input signal, we can really hear that there are some parts of the harmony that are missing. And another thing that we hear from the sonification are also some pitch jumps to higher frequencies, just as we had for the late dip. To conclude this third part of the presentation on multi-pitch streaming, we evaluated, or we trained the units for multi-pitch streaming, and we replaced the typical square filters by vertical filters in one of the layers in the encoder and the decoders. And we obtained a better performance, significantly better performance using the vertical filters than only using the square filters. And in the evaluation on the barbershop quartets dataset, we found the harmonic unit to outperform the baseline in terms of voice specific measures. And in terms of limitations, the multi-pitch streaming system shares the same limitations in terms of data, training data that we had for multi-pitch estimation, because we're using the same data set. So we are only using artificial mixtures of stems for training, and the data set has redundancy. We've also seen in this last example that the outputs of the harmonic unit have some pitch jumps and discontinuities that could potentially be improved by post-processing further. And the main limitation that I identify from these models is the harmonic unit is a very large model, so it has 32 million parameters. And just for reference, the late deep CNN that we just presented for multi-pitch estimation has over 700,000 parameters. So seeing the size, of course, the task is more challenging, so we might need a larger network, but the difference is really, really, really large in this case. So seeing the size of these models, we decided to explore ways to approach the task of multi-pitch streaming following a modular approach, where in the first module, we would use multi-pitch estimation, and then in a second module, we would develop models for voice assignment. And we had the hypothesis that approaching this in a modular way would allow to use smaller models, and also smaller models in combination, combining the two modules. And this brings me to the fourth part of this presentation, where I will talk about our work on voice assignment. So in this case, we developed, as I was saying, a modular approach to multi-pitch streaming. So we first, given an input audio recording, we run the late deep model. So this is the first module where we predict the pitch salient representation, the polyphonic pitch salient representation. And then we developed two different deep learning networks for voice assignment that take the polyphonic salients as input and output four monophonic salient representations, as we've seen for the unit, which follows the same procedure in this case. And then each of these monophonic salient representations is post-processed and converted into the four independent pitch contours that we want at the final output of the full pipeline. For voice assignment, we require a dataset that is very diverse in terms of musical material, because the models need to learn how to separate a polyphonic stream into the corresponding voices. So the more different melodies and different relationships between voices that the dataset, the training dataset has, the better the model will learn how to perform the task. And then following this, we also realized that the modular approach also allows us to train a voice assignment model from salients to salients, so from polyphonic salients to monophonic saliences, instead of using audio. So this, combining these 2 points, we decided to create and release a dedicated dataset for the task, the Synth-salence choral set, which we created by collecting 4-part choral scores from public domain archives, specifically from the Choral Public Domain Library. And for this dataset specifically, we collected over 5,000 scores in music XML format, and then we converted them into our input and target representations. And how did we convert them into our representations? So given a music XML or a MIDI score, we first separated the tracks because we wanted to create the targets and the inputs for each of the targets for each of the tracks separately for each of the voices. And then we first converted the score to a pitch contour, which is what we see in the first figure, these flat lines, because we are dealing with MIDI scores here. And then to try to make the target representation and the inputs more realistic or closer to what we would get from a singing performance, we decided to add some noise to these trajectories. This is what we see in the second figure. But this is a very noisy pitch contour. And then to smooth out a bit this noise, we apply the median filter, and then we obtain something similar to what we see in the third figure, which looks slightly more similar or slightly closer to a real pitch contour from a singing voice, but clearly still looking slightly synthetic. And then this is the pitch contour that we used following the same method that I explained already for multi-pitch streaming and estimation. We calculate or we convert these contours into monophonic salient representations, and these are our input features and targets for the voice assignment networks. So we designed 2 different networks for the voice assignment task, and we compared them. Both both networks have at the beginning one convolutional branch, which is depicted in red in the figure, and then they both go to 4 separate branches, one each of them in charge of estimating the corresponding salient representations for each of the voices. And in these separate branches is where these 2 networks differ. So the voice assignment CNN has convolutional branches. So the 4 separate branches also have only convolutional layers. And the second network, the voice assignment CLSTM, instead of having fully convolutional layers in the 4 separate branches, it includes convolutional LSTMs. So this was an attempt to incorporate some recurrence in the network to try to model some temporal patterns from the input signal to yield smoother pitch trajectories at the output. So these are the 2 networks that we propose. One is fully convolutional, and this one is half convolutional, and then the 4 branches have convolutional LSTM layers. And at the end of the method that we propose, we post-process the pitch, H monophonic pitch settings representation. We find the highest peak, and then we threshold the, the peaks, and if they are above the threshold, then we output them in the output pitch contours. We conducted several experiments for this task, and the first thing we did was comparing the 2 networks that we proposed, the CNN and the CLSTM. And the first comparison we did was just comparing their performance on the synthetic test set from the test partition of our working data set. And in this case, we found both networks to have practically equivalent performances. So from this experiment on synthetic data, we couldn't choose one of them to be better than the other one, but both outperformed the baseline based on hidden Markov models that we were using. So we kept both models for further experiments. And in this case, I'm showing here the summary of the results when combining the late dip as a first module for our modular approach with both of the voice assignment networks and applied to the barbershop quartets dataset also, so that we can also compare the results with the modular approach to the harmonic unit and to the vocal 4 baseline. And what we see here is that the first thing, actually just following the previous results that we've seen, is that the bass voice is the one that obtains the best performances, because the bass usually sings, or almost always sings, the lowest pitch, so it's easier to assign always the lowest pitch to this voice. And then for the other 3 voices, we found that the modular approach combining late dip with one of the 2 proposed models for voice assignment outperforms the harmonic unit and the baseline, the vocal 4 baseline. Then we also combined, following the same kind of evaluation methodology that we used for multi-pitch streaming, we combine the independent outputs into a multi-pitch stream, and we evaluate against multi-pitch estimation ground truth. And now we can compare also, in terms of multi-pitch estimation, the performance of the modular approach to the harmonic unit and to the late dip and the multi-pitch estimation baselines. And in this case, what we see also is that the modular approach outperforms the harmonic unit. So the modular approach outperforms the sort of end-to-end approach to multi-pitch streaming that the harmonic unit offers, and both networks obtain an overall performance which is the same as the late dip, only for multi-pitch estimation. This is an example of the output on the same input recording that we've been seeing throughout the presentation for the other tasks from a song from Cantoría. And this is specifically the output of the modular approach that combines late dip with voice assignment CNN. Let me play the input example just once more for reference.
Y oiremos que mañana ayunaremos por honra de San Antruejo paremos.
In this case, we can focus, for instance, in the same 2 parts that we highlighted for the harmonic unit. In the first note that we see here is mostly correctly predicted. There's some noise here from the alto in the soprano note, but in general, it's better than what we saw in the previous example from the harmonic unit. The second note is also, in the second note, the alto and the soprano are mixed in predicting the soprano note. And then consequently, the same happens here with the alto note and the tenor, especially in this short note here. But in general, the voice assignment CNN is slightly better in this specific example here than the harmonic unit was. But when we look at the unison, what we see here is that this unison is predicted mostly in the soprano voice, and then the alto is actually predicting the tenor note here, and then the tenor is missing some parts of the note also here. So the voice assignment CNN in this example in particular is slightly better for this, but not better for the unison. And we can hear also the sonification, where if we listen very carefully, we will hear some missed pitches, but in general, the combination of all voices together results in a quite normal performance when we sonify it. What we do here in this sonification are also like pitch jumps with very high frequency, high pitched values here that we don't necessarily see them in the plot, but when we sonify the outputs, this is really perceivable. So this is also one problem for the voice assignment networks that we propose. As a conclusion for this fourth part on voice assignment and modular multi-pitch streaming, we created and released the Synth-salence choral set, which can be extended with more scores easily. And then we found that the modular approach to multi-pitch streaming that combines first a multi-pitch estimation algorithm with voice assignment outperforms the baselines. When we compared the two networks that we proposed, the CNN and the CLSTM, we found that they have practically equivalent performances, especially on the test set. And very interestingly, what we see in terms of the model size is that when we combine the late deep with the CNN for voice assignment, we end up with a combined size, network size that has less than 1 million parameters. And when we combine the late deep with the CLSTM, we have a combined size of 2 million parameters, which is significantly smaller than the 32 million parameters from the harmonic unit to approach the same task. So the modular approach that we are proposing here does not only perform slightly better than the harmonic unit, but it's also significantly smaller in terms of model parameters, which is what we were looking for when we started working on this approach, actually. In terms of limitations, the voice assignment models are mostly trained on synthetic data, so this is one limitation. We've seen in the examples that they are also not capable of handling unisons correctly. And we've also seen that they have some the outputs have some pitch jumps and some discontinuities that should be taken care of in a further post-processing probably. In terms of these pitch jumps, I have an example here that shows the difference between the CNN and the CLSTM for this. In the left part, we see the outputs of the CNN for voice assignment. And if we focus on the bass voice specifically, we see quite a lot of pitch jumps here. And if we look at the same exact at the output of the CLSTM for the same exact input signal, what we see is that the pitch jumps are largely reduced. So most of them disappear. This happens with all the voices actually, but it's especially visible in this example for the bass. So this example suggests that including some recurrence in the network might help to have a better continuity in the outputs. And now we arrive to the last part of the presentations, which are the conclusions, where I will try to summarize and point to some conclusions and limitations of our work. We contributed to research on choral music with open data. So we specifically created 4 multi-track datasets of vocal music with different annotations, different songs, different microphones that are publicly available for download, plus 1 synthetic dataset for voice assignment based on pitch salience that can be easily extended with more scores. We also contributed to this research field with data-driven models for pitch estimation, multi-pitch estimation, multi-pitch streaming, and voice assignment, specifically with deep learning-based models. And we also conducted experimental studies on the characterization of vocal unisons, specifically on pitch dispersion. And although I didn't talk about this specifically during the presentation, this is included in the thesis. And in terms of limitations and future work, when we look at what has changed between when we started this research and now in terms of datasets, we see that now we have 4 new multi-track datasets that we can use to advance research on vocal music, but they are still limited in size, in song diversity, and in number of singers. We've also seen throughout the presentation that the outputs of our models for multi-pitch estimation, streaming, and assignment have some post-processing problems. So we've seen some pitch jumps and discontinuities in the outputs. During the thesis, we mainly focused on the models and we focused less on the post-processing, but we did already some experiments replacing the post-processing with Viterbi decoding, and this improves the output pitch contours slightly in terms of they are smoother trajectories. but more research on this side of the pipeline would be necessary to really improve the performance overall. And the main limitation that our models for streaming or for multi-page streaming and for voice assignment have is that they are fixed to 4 voices. So this makes sense because in this thesis we focused on vocal quartets mainly, so SATB ensembles. So we only needed 4 voices. But if we want to predict the frequencies that the singers from a vocal ensemble that has more voices produce, the models wouldn't really work because they are trained for 4 voices. The architectures have 4 branches, so they would fail in predicting the frequencies when there are more than 4 voices in the input. In terms of next steps and future work, or future work directions, one future work direction that I see is working on node segmentation, on segmenting the F0 trajectories to move towards the automatic transcription of choir recordings. And a second future direction that I see is using the output pitch contours to guide performance analysis algorithms. Now I will summarize the thesis outcomes and contributions. First, in terms of data and software, we released 5 publicly available datasets. They are online already and can be downloaded. And we also released 3 open source repositories with pre-trained models and code to run and to use the models to predict with your own audio files. And during this thesis, we also published several papers. In particular, we have 3 journal papers. 2 of them have recently been accepted, so they are not yet available, but will hopefully be available soon. 4 main peer-reviewed conference papers, 2 ESMUC papers, 1 SMC paper, and 1 ICMPC paper. And we also have some other publications, mostly related to the Trompa project. And I want to finish this presentation, I want to conclude saying that rather than perfect models for one task, during this thesis, we addressed multiple tasks that are connected to each other, and we introduced deep learning techniques to this context of vocal music for the first time. And we hope that our efforts to generate new data and new data-driven models enables further research on the topic. And this concludes my presentation, and thank you very much for listening.